Hi everyone, thanks for signing up for today's live broadcast on OpenFluor, a new tool in your fluorescence toolbox. I'm Joanne Lowy, Marketing Manager at HORIBA Scientific and moderator for today's event. HORIBA Scientific is the global leader in fluorescence spectroscopy solutions. We offer the most extensive line of fluorescence steady-state, lifetime, hybrid instruments, and microscope-based solutions from compact fluorometers to modular spectrofluorometer systems. Coupled with our wide range of components, software, and accessories, we can create an optimum solution for all needs and budgets. And over the years, we've incorporated the products and know-how from Specs, IBH, Giovanni Von, Photon Technology International, and SLM, the dominant names in fluorescence spectroscopy. This webinar will focus on our new tool, OpenFluor, which facilitates qualitative interpretation of both fluorescence excitation and emission spectra and components derived from parallel factor analyses. OpenFluor also lets you upload published spectral data sets to the database and compare unpublished data sets to the published sets to evaluate spectral matching and component identification. There are a few important announcements before we begin. First, the slides will advance automatically. Next, feel free to ask questions during this webinar. You can submit questions by typing them in the Q&A box on the Q&A widget at the bottom of the presentation window. If you have any technical problems viewing or hearing this presentation, please click on the question mark Help widget at the bottom of your presentation window. Now I'll introduce today's speaker. We're very pleased to be joined today by Urban J. Wunsch, PhD student at the Technical University of Denmark in the section for Marine Ecology and Oceanography. Urban's research focuses on utilizing optical properties of colored dissolved organic matter, or CDOM, as a proxy for dissolved organic matter distribution and dynamics in aquatic environments. Since the connection between chemical and optical properties, and in particular fluorescence, is not well understood, his work aims to resolve the chemical structures responsible for the UV visible spectroscopic properties of dissolved organic matter. He's studying the links between mathematically decomposed fluorescence spectra of CDOM, those of pure organic compounds, and size-dependent optical and molecular properties of dissolved organic matter in various aquatic environments, such as Arctic fjords, boreal lakes, and temperate rivers. Now I'll turn the presentation over to Urban.
Yeah, hi everybody. Thanks, Jen, for the nice introduction. So today we'll have a webinar on OpenFluor. Before I get started, I want to acknowledge two of my collaborators on this particular project. They're both my PhD supervisors. One is Colin Stedman, and my co-supervisor is Kate Murphy. Colin Stedman works as an associate professor at the Technical University of Denmark, and Kate Murphy works as an associate professor at Chalmers University of Technology in Sweden. Before we get started, I want to quickly remind everybody of the focus of this webinar. First of all, we're going to split it into 4 parts. First, we'll talk about the theoretical and practical aspects of fluorescence spectroscopy to have a common base to advance further into the field of OpenFluor and spectral matching. Secondly, I'll demonstrate OpenFluor, the website and the database with all of its features that are currently available, so that you can then afterwards, after listening to the webinar, simply go to openfluor.org and try it out yourself. Third, we're going to take a look into the engine room of OpenFluor. So we're going to talk about the fundamental aspects of the assessment of spectral similarity. And lastly, I've chosen 3 example studies to demonstrate OpenFluor and how you could benefit in your own line of work and in different application fields. So to demonstrate the fundamental aspects of ultraviolet visible spectroscopy, I've chosen an example out of my own line of research. We all focused on dissolved organic matter, or DOM, which is a complex pool of organic compounds that you can find basically everywhere on Earth. So they're also contained in wastewater, drinking water, and all other aquatic systems that you can imagine. Dissolved organic matter, like I said, is made up of a lot of organic compounds, some of which contain conjugated double bonds. So they have alternating double bonds and single bonds in their molecule, which makes them more and more likely to be part of what we call a colored DOM. So this is also called CDOM, or CDOM for short. This is the part of the DOM that makes your tea and coffee go black or brown, and this one river have this funky yellow color that you can see in the picture here. What these compounds do is they simply absorb light in a two-dimensional representation you can see here. So we can simply see the spectrum of UV vis from 240 to 600 nanometers, and we can see how this particular compound in this example absorbs light from 240 to about 340 nanometers in that range. Some compounds also contain aromatic moieties, so they have these aromatic rings, and some of them are also conjugated, like the example here, and such compounds are more and more likely when you add more and more of these aromatic rings and conjugations, more and more likely to be also part of what we call fluorescent DOM, or FDOM, or FDOM for short. So that's what makes these beakers here go in bright fluorescent colors. Usually fluorescence is much shorter in its lifetime, so it's on the scale of nanoseconds in its lifetime. The two-dimensional representation of this process is shown here. You can see the absorbance of this fluorescent compound in the solid line, so pretty similar to the absorbance example, but besides absorbing light, you can also see the fluorescence emission at the higher wavelengths, so that is lower energy, peaking at about 410 or 420 nanometers in this example. But instead of looking at this two-dimensionally, we can also simply multiply these two spectra together, and we end up with what's called the emission excitation matrix, or IAM for short. And this is how we're going to look at fluorescence spectroscopy spectra today. So let's talk about the IAM data processing. We're going to assume that you've already collected a bunch of samples and measured them in your fluorescence spectrometer, and now the question is how to process the data. Data processing can be divided into 4 parts. First of all, we need to import the data into the software of our own choosing. We here use MATLAB to process IAM matrices, but in principle you can also do it in other software as well. Secondly, we need to ensure that we correct for biases that occur during the measurement of IAMs. So we need to ensure calibration using either reference materials such as quinine sulfate or other standard reference materials provided by NIST. And also we need to account for inner filter effects, so that is the reabsorption of light as a consequence of fluorescence. Third, we need to remove scatter, so the physical scatter called Rayleigh and Raman scatter. And fourth, we need to calibrate our IAMs. That is, we need to make sure that the units, the fluorescence units that we record and that are unique for every single instrument, are calibrated so that we can compare different results of different spectrophotometers. I'm going to quickly show you how this looks in practice. So once we imported the data, you can see that we don't see much, except we see a little bit of noise on the lower right corner, and we see a scatter line in the lower left corner. So the second step was bias correction, that is the inner filter effect correction. Here you can see a contour plot of the calculated inner filter effect based on the absorbance. So it's quite useful to have an instrument like the Aqualog that contains or that collects simultaneously the emission excitation matrices as well as the absorbance spectra in the same instrument at the same time. So you can use that data to then calculate the amount of inner filter effects that occur at different wavelengths, and this example shows a quite extreme case where we have an inner filter effect of about 40% at the lower wavelengths, that is 240 nanometers in this case, and they become less and less important the higher the wavelength in our example here. But in principle, it's important to remember that as long as you have an absorbance of higher than 0.04 per centimeter, the inner filter effect will be more than 5% in your sample. And that is at any wavelength, not a particular wavelength that you choose, but any wavelength that you consider for the EAMs in further processing. So it's quite important to look at your absorbance spectra and see if inner filter effects are a problem for you. If so, they're really easy to take into account. The third process is the most visually appealing process. Here we remove the scatter, so that is first and second order Rayleigh and Raman scatter. And after the removal, and in our case we also interpolated in this example, you can clearly see the EAM fluorescence of our quite low concentrated sample here. This is why it wasn't really visible, its fluorescence wasn't really visible in the data import step in the contour plot on the top left. But after scatter removal, you can clearly see the fluorescence of the organic compounds in our sample. And the last step, the normalization, the only thing that changes here is the unit of the color bar. In step 3, we had arbitrary units that totally depend on the fluorescence intensity. That is a function of the excitation light that comes into our sample. And after step 4, we normalize this signal to what we call Raman units, so the Raman area under the peak at excitation 350, emission 397. After successfully measuring and correcting our data, the question now is, if we have complex mixtures that we measured, how do we obtain fluorophore spectra in this complex mess that we're working with? And this is where ParaFAC or parallel factor analysis comes into play. You can imagine your emission excitation matrices as well as the multiple samples that you've just collected as a three-dimensional cube. You have emission and excitation on one side, and you have a gradient of some sort on the other side. So that represents your multiple samples. That can be an environmental gradient, or a treatment process, a production process, a monitoring process, or all sorts of other applications that you personally can imagine. This is in what we call a three-way dataset, a three-dimensional or three-way dataset, and this is perfect for multivariate statistics approaches such as ParaFAC. In order to understand the ParaFAC algorithm, we're going to take a step back, and instead of looking at complex mixtures, we're going to demonstrate this on a simple fluorophore that can also be modeled using ParaFAC. A simple fluorophore, one single fluorophore, is represented by emission and excitation spectra. So that is B1 for the emission spectrum and C1 of the emission spectrum of this single fluorophore. And the product of both equals Z, which is the emission excitation matrix of this particular fluorophore. However, this fluorophore also, the fluorescence intensity also varies with concentration, so that we also need to include a concentration term which is called A1. So the emission excitation matrix equals the product of A1, B1, and C1. But since we're dealing with a matrix, we can rewrite this whole notation in a different form and simply represent the fact that we're measuring multiple emission and excitation wavelengths. And of course, the concentration doesn't vary with emission and excitation wavelength, at least we assume that. But the emission and excitation loadings at every single wavelength will differ for every fluorophore. So this is basically what's behind ParaFAC. And ParaFAC in its entirety, it models according to this formula here. So on the left, we have the measured data. That is the number of samples, the number of emission and excitation wavelengths that we just recorded. And the model data is described as the sum of a number of components that you personally have to determine. And these components, each individual component has a concentration A, a number of emission spectra or emission loadings B, and a number of excitation loadings C. Besides modeling our EAM, this formula will never come up with a perfect representation of the EAM. so that the model also contains residuals, that is, unexplained data such as instrument noise or random spikes in our sample, or also leftover physical scatter, Rayleigh and Raman scatter that we didn't properly remove, contrary to what we thought. So, just for full disclosure, ParaFAC makes a number of assumptions which you need to know in order to know whether or not you can use ParaFAC to mathematically decompose your EAMs. First of all, we have a variability assumption. So that basically says that two fluorophores can never occur in the same exact concentrations with the same exact emission and excitation properties. Secondly, we also assume trilinearity. So that means that emission spectra are invariant across excitation spectra, and excitation spectra are invariant across emission spectra, and that the fluorophore concentration increases approximately linear with the fluorescence intensity. Third assumption, additivity. So if we add a number of components together, a number of fluorophores together, we assume that they're chemically isolated and that the sum of all individual fluorophores also equals the summed EAM that we measure in the spectrophotometer that we choose to characterize our sample. So there's no quenching, no interaction between those fluorophores occurring. And fourth, that's a quite important one as well, knowledge of your sample. So if you have a rather simple sample, let's say you want to characterize a pill that you just produced and you know there's only 3 components in there, you can assume ParaFAC to model 10 components. And the other way around, if you have a very, very complex sample, you can't imagine or you can't expect ParaFAC to properly model this data with a very low number of components, 2 or 3 components. So you have to assume that there's more going on than just 2 fluorophores in a very complex sample. So let's take a quick look at the ParaFAC approach to modeling. So the practical sort of sequence of things that you have to take into account before coming up with a valid ParaFAC model that you can then use to interpret your data. This approach is basically split into 2 parts. One is the data exploration phase, and the second one is the model validation phase. In the first phase, the data exploration, we fit a number of models, and this can be a quite long process, can be quite annoying sometimes, where you have to go back and forth a lot, but in the end it'll be very much worth it for the model validation phase. So the first step is that we fit a number of components, a number of ParaFAC models to determine outliers. This is samples that are either highly contaminated or contain other problems in themselves, so that they don't really represent the entirety of the batch of samples that you just measured. So they should be removed, or at least you should consider removing them in order to obtain a valid ParaFAC model that describes the majority of your samples. So after this step, we then go on to fit different ParaFAC models with different number of components, so that for DOM, for example, for FDOM, that usually ranges from 2 to 10 components. And we simply observe how ParaFAC models with increasing number of components. We observe how it first underfits the data, so it doesn't properly represent the complexity, and then at the high end we need to observe that it overfits the data, so it starts fitting random noise and the components don't look nice anymore. Typically, one of the number of component models will look best, and this is the one to go forward with. The third part in the data exploration phase is then an iterative process. So after arriving at what we think is the right number of component model, we take a look at the samples, and we might have to remove further outliers or some wavelengths that are rather noisy or don't contain any information. So this can be a lot of back and forth here, where we then have to reconsider the suitable number of components. Maybe that's just changed because we removed additional samples, and so on and so on. But generally speaking, at some point we're going to arrive at a model that we're generally happy with, And then we should step into the phase 2 model validation. We first of all need to consider the residuals. So do the residuals resemble a distribution that is random, or is there structure in the noise? What's the overall magnitude of the residuals, and so on and so on. Once we're happy with that, we need to take a look at the loadings of the ParaFAC components. In other words, do they represent fluorophores that are typical organic fluorophores, or do they have some loading that doesn't really represent typical fluorophores, in which case you should question whether or not ParaFAC, or this particular ParaFAC model, is a valid one. The last step is the so-called split half validation, where the dataset gets split into two halves with random combinations of samples. And these combinations are then modeled independently, and the assumption is that a ParaFAC model is only valid as long as we arrive at the same solution within the splits and also in comparison to the overall model. And this is the typical ParaFAC modeling approach. So if you want to take a more in-depth tutorial to this ParaFAC modeling, you can. I'll refer you to this paper by Caitlin Murphy, Colin Stedman, Daniel Graeber, and Rasmus Bro, where they published a paper in Analytical Methods in 2013 that details all of these things that I just said for you to go and have your own look. So generally speaking, we've just decomposed our EAMs of a dataset of any size, really, that contains emission and excitation information of a number of samples. And in this example here, we've just arrived at a 5-component model, the ParaFAC model that we're happy with. But the question is really, what's next? So really, what do these components then tell me? And this is where the OpenFluor database comes into play, because it allows us directly, without further processing, to compare our own ParaFAC model to every single ParaFAC model that's in the database, and it allows us to then benefit from the previous knowledge of those studies that these models came from. So the next step is just a short demonstration of the OpenFluor database. Okay, so now I will give a short demonstration of the OpenFluor database. We can navigate to this website by simply typing in openfluor.org in any kind of web browser that you can imagine. And the first thing we see is the homepage of the OpenFluor database, where you can have some basic information on what kind of data it currently accepts for publishing, and what you can do with the website, and also some further information on how to cite OpenFluor and how to use it as well. The first thing I want to draw your attention to is the login page. So if we use the login button on the top right, you get to the login page where you have to supply a username and password to get full access to the database. If you don't have an account already, you can simply click Create an Account, supply a username, email, and password, and you'll be done with the registration within a couple of seconds. So let's just use my username and password combination to log in and have full access. So after login, you will be taken back to the homepage of the website, and you see first of all all the different sub-websites that you can navigate to, such as the About website, which is the homepage. You can look at the datasets, you can query the database, watch a demonstration, even submit a new dataset, or look at your models that you already submitted, as well as change settings in terms of spectral matching. So let's take all the functions of the OpenFluor database step by step. First one, datasets. So we can browse all the datasets that are available in the database. Here, if we just show the first 100 entries, we see all the studies that have been published in the database. This is an interactive table showing the complete reference to the study, its ID number in the database, and the date it was submitted, as well as a link to the overview to get all the detailed information on each and every study. So this table is actually interactive, so we can sort it by ID number, we can sort it alphabetically by the name of the first author, and submission date, which is essentially ID number. So if we click on a random study here to get to an overview, we get the information for every single database entry, such as name of the study, the creator of this data set, and the upload date, as well as a complete reference and some information on the username of the person that uploaded it, a contact information in case you want to contact this person to ask about this study, and then also a DOI to get to the study directly. Then also some information on the fluorometer that was used and the units, as well as some constraints on the model, and some information on water source and ecozones of this particular data set. Also then on the bottom, the last thing in this overview per study is some information on the ParaFAC modeling. So how was the model validated? What were the methods used? How was pre-processing done? And a basic description of this model. So this information you will find for every single entry, and it'll be a great tool to get all the information that you need in case you are interested in any study in the database. So on to the next feature, which is called querying the database. So this is the main feature that you're going to be interested in if you just simply want to use the database to compare your own fluorescence spectra or ParaFAC spectra to the datasets that are already contained in the database. So we simply hit Query the Database in the top tab to navigate to the Query Database website. We have to choose a file and then run the query. So we choose a file, in this case example-spectra.txt. This is an OpenFluor compatible text file that contains the spectral information on the fluorescence spectra we want to compare. It looks like this. We have different columns and a lot of rows. We have either excitation or emission loadings, the wavelength information, and the loading information, so the intensity of this particular component. Then we have component 1, 2, and 3. So this is the model that we're going to use as an example, a 3-component ParaFAC model. We simply open this text file and run the query. Don't be surprised if this takes a little while, because usually we have a lot of components to compare against. Hundreds of ParaFAC components are already in the database, and the more components you compare to, the longer this is going to take. Once this query is complete, you see this information. We have 3 tabs. First of all, matching results, spectra, and graphs. And we're going to go through all of these tabs one by one. The matching results overview tab shows you a first overview over all the database entries that have matched with one or more spectra of the spectra text file that you just uploaded. So for example, Shark Bay is the first database entry that matched with a component in our own spectral text file. So we can click Show Overview to get to the dataset entry information, who uploaded it, what's the web email address, what's the DOI of that paper, and all sorts of other information on this particular study. Going back and scrolling down, we can see for each and every match the information on the study that matched with our spectrum and how many components this model has, in this case 4, in this case 7, and what which of their components matched with one of ours. So in our case, component 1 matched with component 2 of Shark Bay, component 2 matched with component 3 of Shark Bay. And this is going to be in this table view for each and every one of those matches. So this is a lot of information to digest, and the number in this table represents the similarity between Shark Bay and component 1 of our own spectrum. The next tab, Spectra. This is quite the powerful tab where you can see a similar representation, but this time of the results, but this time ordered by then a component number of our own study. So the first table contains component 1, the second table component 2, and the third table component 3. And then in the columns we can see the spectral loadings of the component that matched in different studies with the component 3 in our own study. Combined, this information can then be also downloaded by every user in a simple CSV file that you can open, for example, with Microsoft Excel. This is then the overview that you can explore on your own time, on your own computer, anywhere offline. So we get a simple, pretty similar representation of all the matching database entries and the matrix of the first tab, the matching results tab, and then the table view where you can see the detailed information on which database entry matched with component 1 of our own model. And since we're already in Excel, we can use simple plotting tools to get a first overview on our own computer on how these matches actually look. But the database can also do that for us in a first try. This is the Graphs tab. Here you can see a graphical representation of all the matches. So component 1 is quite busy, so we're going to go down to component 3 actually. So you can highlight each individual spectrum to blend to sort of focus on this one, component 3 emission spectrum and its excitation spectrum, for example. So the rest will be sort of blurred out a little bit, and you can focus on the individual spectrum, like so. In this way, you can already screen a little bit on which matches might be good and which matches might be not so good, and you should be careful to say to make any kind of assumption on the similarity. Now, this brings up an obvious fact. So what does this database bring up with regards to similarity? So what's the threshold, and how can you set this threshold? You can simply hit this button here. This is the preference button where it says Hello Urban. You're able to modify your settings here, and the only setting that you can modify is the minimum similarity score. By default, this is the lowest value you can set, but you can also just set this to a much higher value and hit save, and then we'll just repeat this match, run the query again, and we see with this threshold we get only 2 matches. So much less, but the quality of those matches is obviously higher. So the next feature of the OpenFluor database is called Demo. You can go to this feature here. This is going to be interesting if you just want to replicate what we've just done and try out the database for yourself. You can simply hit this Run Demo on example-spectra.txt button, which is going to take you to the exact same website that we've just seen, the same exact page, where you can simply just test out the functionality of OpenFluor and just do a test run yourself. But since we've just done that, we're going to go on to the next feature, which is called Submit New Dataset. So this is a feature to be used with caution. Currently, the only users allowed to submit new datasets are users that can verify that the spectra that they're uploading have been going through a peer review process. Otherwise, you shouldn't be uploading data sets on your own. Then the next tab is called Models. In this tab, we can see that I've personally uploaded 2 spectra of a paper from last year, where I uploaded organic compounds and their fluorescence spectra to the database of simple organic compounds. But in principle, this table can go as busy as you get. And you can then also show or let yourself show or be reminded of what you've done in the past. So you You can also then click Export the model in case you lost it on your own computer. Click on an overview of the model, the excitation spectra, and the emission spectra. The last tab we've already been to, the Settings tab, where you can modify the minimum similarity score for a query for the database. So these are all the features of the OpenFluor database. Yeah, like I said, just hit Demo, try it out yourself, and see what it can do for you. So after this short demonstration of the OpenFluor website and the OpenFluor database, it's now time, as I said in the introduction, to take a step back again and take a look into the engine room of OpenFluor. In other words, how does it assess spectral similarity, and how does it tell us that two ParaFAC components or two ParaFAC models are incredibly similar? This is where the Tucker congruence coefficient is used, or TCC for short. The Tucker congruence coefficient simply compares either emission or excitation loadings of a ParaFAC component between different models. The formula that it does it with, you can see here. So it's a simple, a rather simple mathematical comparison of the spectral loadings, and you get a simple number, a single number, that will then tell you how similar these two components are. But of course, when we compare components, we can't just either look at emission or excitation. We have to consider both and the combination of both, so that the overall Tucker congruence coefficient when comparing two components is the product of TCC for the excitation and TCC for the emission. This TCC, the congruence coefficient or the similarity coefficient, can range from 0, which would mean that two components have absolutely no spectral resemblance whatsoever, and 1, which would mean that we're dealing with a perfect match here, and these two components are very, very similar indeed. In principle, we should only consider a TCC with a threshold of 0.95 as a minimal match criterion in order to speak of spectral similarity between components. But, as I'm going to demonstrate to you, visual inspection is immensely important for the verification process of this assessment. And that is also an integral part of the database, right? If you remember how we could visually inspect the matches that the database would come up with, this is where this part comes into play. So, to demonstrate, I'm just going to show you two different animations where we simulate changes in the excitation and the emission spectrum. So you're going to watch two curves here. The black curve that you can hardly see in the starting picture represents an unchanged component, and the red curve will change slightly to demonstrate how the Tucker congruence coefficient will slowly change as a function of the spectral change of the simulated change. So first of all, in the top row, the excitation spectra changing. As you can see, we're slowly changing the red component, and the TCC goes down from 1 to 0.95, 94, 93, and so on and so on. Then, if we change the emission spectra, you can see here simply a shift between the peaks. So the red curve slowly moves to higher wavelengths, and the TCC goes down and down and down. But how different can chemically similar fluorophores appear in fluorescence spectroscopy? To assess this, we've conducted a study last year where we measured 14 different organic compounds, part of which were tyrosine and tryptophan, and their fluorophores cresol and indole. So how similar is the fluorophore of tyrosine compared to tyrosine? As you can see here, we have both loadings of tyrosine and cresol, and they're just slightly shifted, similar to the example I've just showed. And you can see that the similarity is quite high with 0.96, but we know for a fact that these two spectra are not the same. So this is why you always have to take or have to be cautious when using TCC to argue for spectral identity of two ParaFAC components. And similarly for tryptophan and indole, the shift is a little more pronounced, and as you can see, the similarity coefficient goes down to 0.95. But this is already a little bit of a warning sign to you not to use 0.95 as a rigid threshold to report spectral identity, but to consider a much higher Tucker congruence coefficient if you want to really make valid assumptions for your study using previous studies done by other researchers. So also the visual confirmation part is important. I'm just going to show you, like I said, the visual confirmation is important. I'm just going to show you a couple of examples here. First, good examples and then bad examples. So as part of this study, we measured, like I said, 14 different compounds, and we compared them to ParaFAC components in the OpenFluor database. And you can see a number of good hits for tyrosine. The pure spectrum is always displayed in orange and the ParaFAC spectra in black. You can see a number of good matches in the OpenFluor database for both tyrosine and salicylic acid, but for other organic compounds like coumarine and benzoic acid, we didn't really find good matches. They're quite similar, but if you consider the scale from 240 nanometers to 600 nanometers, there's quite substantial shifts going on between these components here. So yeah. And also, what you're going to have to deal with is when you match OpenFluor components to your own components is instrumental variation versus differences in real differences in compounds. So in the top panel here, you can see ParaFAC components that are in the OpenFluor database. Two different sort of group of components. On the left, components that are very, very similar, and on the right, components that differ a little more. But how much do they actually differ? For that, we're going to just take a look at the emission spectra. And in the left example, you can see that the maximum difference between the peak maximum in the emission loadings is only 2 nanometers. And that is well within range when you consider that different instruments might be changing or might be different with relation to their calibration, the spectral calibration. But in the right example, we see that the differences are 14 nanometers. That is well beyond the variation that you can expect from instrumental variation, and implies that there might be a difference in chemical composition of these ParaFAC components. Now let's move on to the final part of this webinar, which is a demonstration of OpenFluor and its usefulness in different application fields. For this, I've chosen 3 examples, one from aquaculture, one from water treatment, and one from drinking water and contaminant tracing. All of these studies are already available in the OpenFluor database, so if you like a particular study, you can go to openfluor.org and find them there and read up on them. The first example from aquaculture is a particularly recent study published in 2015. So despite being available in the OpenFluor database, it was already able to make use of previously published models that are stored in the OpenFluor database. In their study, Adam Hambley et al. Characterized organic matter from recirculating aquaculture systems using fluorescence spectroscopy of organic matter, and used it to have a proxy for a system state description. So recirculating aquaculture systems have a number of challenges they face. First of all, operators want to minimize the cost and of course also minimize the risk of a failure and maximize the fish quality and also the fish yield. So it was investigated whether or not fluorescence spectroscopy and ParaFAC models can be used to describe the system state and basically predict and prevent system failures that would be a catastrophe for the return of investment in aquaculture. So in their study, they found a 5-component ParaFAC model that they then compared to the about 70 models that are already published in the OpenFluor database. And for 4 out of the 5 components, they found significant matches or significant similarities between their model and other models. So in this table, you can see components 1 to 5, F1 to F5. F1 is the component where no matches were apparent, but F2 to F5 had significantly similar components in the database. And the matches they found were linked to freshwater lakes, saline lakes, rivers, estuaries, marine waters, drinking water, and also agriculturally impacted wetlands. So quite interesting in terms of their ability to describe the system state, because the organic matter was a good proxy to describe the system overall, because they used marine or saline water to fill up the tank, and they used tap water to dissolve the fish feed, as well as they found seemingly ubiquitous reaction intermediates of organic matter. So they were already, just by using OpenFluor, able to describe their system in a sufficient manner. On top of that, they also used these components to trace dynamics in their system that they, of course, were able to control. So they found that component 1 and 2 correlates to fish input and system production of organic matter. Component 3 was correlated to tap water used for the feed for the fish. And component 4 was indicative of organic matter produced in the system. And component 5 was then indicative of the actual feed input used to feed the fish. So this already demonstrates how you can build on top of previous knowledge that is contained in the OpenFluor database to make use in aquaculture systems. On to the second example, which concerns water treatment. Water treatment facilities ideally need a comprehensive knowledge of processes, if possible, in real time. Traditional parameters include total organic carbon, or biological or chemical oxygen demand. Some of these parameters take quite some time to measure, and the sensitivity of these measurements is not quite as good as managers would hope. But it's been found for some time now that organic matter fluorescence correlates nicely with some of these key parameters that take a lot longer and less to measure and are less sensitive in comparison. So the question really is, can we use a simple global ParaFAC model to describe a number of these water recycling facilities, or do we need to come up with a model for each and every single plant? And does each and every single operator need to put in this time to describe their system comprehensively? Kate Murphy, in her study, found that nope, that's not necessarily the truth. She found for Australian water recycling plants that she can come up with a global 7-component ParaFAC model that you can see here that comprehensively describes the organic matter fluorescence of all of them. There's only been, in this study, she only found that there's only a few components that don't sufficiently overlap. So this is the global model, and these are the detailed characteristics of these components with respect to their excitation and emission maxima, but also a description of them. So terrestrial humic-like fluorescence, microbial humic-like fluorescence, also component 3, for example, a wastewater nutrient-enriched component that traces processes involved with that, protein-like components, and so on and so on. But more importantly, she also found out that some of these components are already well represented by not decomposing mathematically the EAMs, but just looking at the raw EAMs. So for example, component 3 correlated with an R-squared of 0.99, so very well with the raw EAM without the need to decompose it, which qualifies this component to be traced by an online fluorescence sensor that can measure organic matter fluorescence in real time. So in case you are running a wastewater treatment facility and you are interested in online monitoring in real time, you can use this knowledge and describe your system using fluorescence spectroscopy in ParaFAC to see if you can find similar components, and if you do, you might be able to benefit from this knowledge and use components that correlate very nicely with the bulk fluorescence of the EAM to then benefit from this and describe your system in real-time online fashion with simple sensors that are inexpensive and very sensitive. On to our last example, which concerns drinking water and the tracing of contamination events. drinking water distribution systems need to be controlled to ensure consumer safety, of course. And the problem is with contamination events that they're often short-lived and intrinsically difficult to detect because of their short-lived nature. But of course they do matter for, these contamination events do matter for consumers because they involve their safety. So the goal here was to assess the organic matter fluorescence and its natural variability over a long period of time, to monitor drinking water distribution networks, and maybe, if possible, establish organic matter fluorescence as an indicator for contamination events. In their study, the researchers have found a 4-component model which did not have a significant amount of variability on a temporal scale. This is what you can see in the bottom left figure here. All of the components seemed rather stable with regards to long-term variability over an amount of weeks to months, but also in terms of their time of day. There was not really a lot of variability here, so that's good news because it means the distribution network's rather stable. But in case contamination events happen, that might qualify organic matter fluorescence to be a sensitive tracer to these events. And this is exactly what they found. They found that the component 4, here highlighted in red in their ParaFAC model, was significantly correlated to the amount of wastewater that was added in an artificial experiment that simulated a contamination event. So that they were really sensitively able to detect minute amount or very low amounts of carbon on the microgram per liter scale, which is a very low amount of carbon in terms of the average sensitivity of a total organic carbon measurement. But the more interesting thing is that in comparison to another component highlighted in red here, component number 3, this component number 4 was not just sensitive but also very selective for this contamination study. Another component did simply not respond to added wastewater, which means that the fluorescence emission of component 4 is very sensitive and highly selective for a contamination event. And that qualifies it because there's not a significant amount of overlap in the fluorescence emission, not just for detailed ParaFAC studies, but also for online measurements. So in case you're interested in drinking water and contamination monitoring, this study is a beginning. It shows that this protein-like fluorescence can indicate contamination events, and if you characterize your own drinking water system and your distribution network with a similar ParaFAC model, you might be able to use the same components to predict contamination events just like they did in their study here. So I hope I was able to demonstrate how you use OpenFluor in practice, how it works in the background, and how you can benefit in your own line of work. Let me allow a quick couple of remarks at the end here. OpenFluor is driven by users for users. We've established the database in the past, but it is driven by user content. So the more people upload in various different application fields, of course, the more users can also benefit from this research. That leads to quasi-unlimited opportunities that are not just limited to the application fields I've presented, but also can expand to a much broader range of fields. For example, contaminants and very specific contaminants and their fluorescence properties could be uploaded to the database, similar to what we've done in the last year with simple organic fluorophores that were more interesting for dissolved organic matter studies. But yeah, so this can be expanded quasi-unlimited. Yeah. Secondly, of course, we will add functionality as the database progresses, as the website makes some leaps. We will expand the functionality in the future to make it even more useful, even more usable for all the users that want to use it in different ways. So let me just remind you again, the OpenFluor database can be found at www.openfluor.org. So feel free to just go there today, test out the demo, see how it works for you, and if If you find any problems with it, just contact me at the email down here, and we'll talk about it. Secondly, that I didn't mention in the webinar, but the text files that we uploaded to the OpenFluor database had to be in an OpenFluor compatible format, which was produced with the Dr. Toolbox. This is a MATLAB toolbox produced by Kate Murphy and Colin Stedman, which you can download at the website listed here. And with that, I'd be happy to take any questions.
Hi, thanks, Urban. That was a very informative webinar. We're almost out of time, so let me just say that we'll answer about 2 or 3 questions that we have, and any others that we've gotten, we can send you an email with the answers. So the first question is, I don't want to use MATLAB since I don't have any experience with it. Are there commercial software packages that support data processing and modeling as well as data export in the right format so I can use OpenFluor?
Hello?
To October of next year, and it'll be posted on HORIBA's site shortly. So again, feel free to listen and forward the link to any colleagues who may have missed today's live event. We look forward to seeing you at our next webinar. Thank you again for attending.